Assalamualaikum. This is our last lecture, video lecture for chapter 4, subject 3562. Okay. So for this topic, chapter 4, we will focus on truss with incline or skew of support. Okay. If a support is inclined or skew at some angle alpha for the global x-axis as shown below, the boundary condition on the displacement are not in the global xy direction, but in the local xy direction. Okay, let me explain to you about this wording. Okay, if a support is inclined, so this is the support, and then it is inclined. It is not horizontal, it's just not vertical, it is inclined. There is an angle alpha at some angle alpha. Okay, that incline relative to the global x-axis. Global x-axis is an angle alpha. Okay, this one. Okay, at some angle alpha for the global axis. The boundary condition on the displacement are not in the global xy direction. So our boundary condition is not in the global xy direction. Okay, in the global direction, global x and y. So our boundary condition is in the local coordinate direction, which is in this case is x prime, y prime. Okay, the local coordinate system. So our boundary condition. What is boundary condition? Boundary condition means displacement, force. Okay. Okay. In this case, we see what is the displacement for not 3 in local x direction and in local y direction. Okay. So basically, we have identified the boundary condition in the local xy direction, such as displacement and force or other displacement. We have displacement not 3 in x local, but there is no displacement in y local. Force contrasts to displacement because not 3 can move in x direction. So force in x direction for not 3 is 0. Okay, but there is reaction force in the y direction. Okay, reaction force that resists to the pressure from this structure. Okay, so we have identified the boundary condition, and then we transform this boundary condition from transform the local boundary condition from one into global system using T star. What is T star? Transformation metric from our previous lecture. Okay, for this case, see, displacement for not 3 in local y direction is 0. Okay, cannot move in y local direction. We transform it into global displacement for not 3 in y direction. Okay, let's see example in the next slide. Okay, so we have the structure. We have not 1, not 2, and not 3. So identify there's an inclined support here. So the boundary condition is somewhere here. Okay, and we also have support here with the roller. So there is also a boundary condition here, although it is not inclined. Okay, so given P is 1000 kilonewton, so there is external P. There is external P in x direction, positive x direction on not 2. Okay, the length of element 1 and 2, element 1 is 1 meter, element 2 1 meter. The material properties, Young modulus for all elements 210 gigapascal. Cross-sectional area for all elements, okay, similar, okay. For element 1 and 2. So for element 3 is 6 times 10 to the power of minus 4 meter squared. So the question is determine the unknown displacement and reaction force. So this is a very general requirement. So determine the unknown displacement, meaning the unknown at the unknown displacement and reaction force at node 1, at node 2, node 3. Okay, determine the unknown displacement and reaction force at node 1, 2, and 3. Okay, so element 3, it is 45 degree from X global axis. Okay, from the picture we can say node 1 is fixed 100%. There's no movement at all. Node 2, there is a movement in X direction, but cannot move in Y direction because there is a constraint here. Okay. Node 3, there is a movement in the local X direction. Local X direction. Okay, and there is no movement in the Y local. Okay, let's see another one. Okay, now we want to establish uh, global stiffness. In order to find global stiffness, we have to identify not the coordinate as far as the L cos theta and M sin theta for element 1, 2, and 3. Okay, not element 1 is this between node 1 and node 2. Element 1, this one, node 1 and node 2. So element 1 consists of node 1, node 2, from smaller number node to bigger number nodes. Okay, element 2, this is element 2. So we take from smaller numbers of node, this is 2 to 3. 2 to 3. Element 3, this one. So we take from smaller number 1 to 3. 1 to 3. Okay, now we see the nodal coordinates, the nodes coordinate. Okay, coordinates for node 1, coordinate for nodes 1. Node 1, coordinate, what is the x value? This is the global axis. Node 1 is located here at the origin of global coordinate system. So at the origin. So x value here is 0. Y value also it is 0. So 0, 0. Node 2. Node 2 is somewhere here. What is the x value of node 2? Obviously it is 0. What is y value for node 2? It is the height of this element, element 1, which is L. So L. Node 3. Node 3. What is the x value? So here, somewhere here, it is this length, element 2 length. Okay, from here to here. So node 3, coordinate x is L, and coordinate y also L. This is the length of element 1. Okay, so we get all the coordinates, know the coordinates for all the nodes. Okay, and now we find we create table of direction cosine. We know L is cos theta, M sin theta. Okay, and L, if you follow from small node number to bigger node number for each element, so we can use this one, x2 minus x1 over L, positive and positive. Okay, now we use let us use this formula first. Okay, to find the L, to find L. Okay, so for element 1, the length for element 1 is L. So length is L, x2 minus x1. x2 minus x1. What is x2? The value of x at node 2. So the value of x at node 2. So 0. So x2 is 0. Minus x1. What is x1? The value of x at node 1. The value of x at node 1. So 0. So 0 minus 0 over L. Length over length. L. 0 per length. So 0. Okay. Or we can use another method. We use find angle. Angle theta. What is angle theta? It's 90. Okay, 90 because we measure from x global to the element 1 because it's element 1, okay, to the element 1 from x global to element 1, the value is 90. So cos 90 is 0. Okay, for m sin 90 because the element 1 again, sin 90 is this one. Okay, if we want to use the formula, this formula, m is y2 minus y1 over L. What is y2? Y coordinate at not 2, y. So L minus y coordinate at not 1. So this one, L minus 0. So L. Okay, y2 minus y1 is L over L. So this one. Okay. Okay, for element 2 is between not 2 and not 3. Not 2 and not 3. Okay, in this case, x2 become x not 3 because it's element 2 is between not 2 and not 3. So for this one, element 2, so x2 now become x3. x1 become x2. Okay, remember there's not 1, not 2 for each element. Element 2, we have 2 knots, not 2 and not 3. So x2 become x3, x1 become x2. Okay, so in this case, x2 minus x3 is this x3 not 3 x value L minus x x at 2, okay, 2 which is 0, L minus 0. L minus 0 is L over L is this one. M for M, L minus L is 0 over L, so 0. Okay, so say if we use angle, so the angle here for element 2, okay, so the angle is 0. Why 0? I show to you later on. Okay, for element 3, so now element 3, this one, between not 1 and not 3. Okay, so not 2, x2, x for not 2 is x3. Okay, x1 for not 1, number 1. So this one is between 3 and 1. 3 and 1. So we take L minus 0. L minus 0 is 0. It is L over L. So over L square root 2 because the length of this one is L square root 2. Okay. So it is, we cancel L. So we get 1 over square root 2. And similar for M. Okay. Let's see. In terms of angle. Okay. In terms of angle, this one is 90 degree. 90 degree. So cos 90 degree is 0. Sin 90 degree is 0. So 0, 1. 0, 1. Okay. Okay. This is cos. This is sin. L cos M sin. So cos 90 degree 0, cos sin 90 degree is 1. 90 degree, the angle from x axis, x global to the element 1, to the element 1. So this angle is 90. For element 2, the angle is 0. See, element 2. Okay, we put the global coordinate axis at the smaller node number. So smaller node here is 2 to 3. 2 to 3. So our global coordinate axis is at node 2. And then we measure the angle from axis to element. So what is the angle? X-axis to element 2. So the angle is 0. Okay. For element 3. So we take the global coordinate axis, put it at element 3, smallest number. Okay. And we measure it from x global to element 3. So it's 45. That's why we get angle 90, angle 0 for element 2, and angle 45. Okay, we can use this formula, or we can use this formula. Okay, okay. Remember, x2 and x1, this refer to the not number here. If you are saying about element 2, so between x3 and x2, because the second knot is not 3, the first knot is knots 2. Okay, okay, okay. What else? Okay, you must know how to create this table. Okay, this table, because we are going to use this value in our formula for stiffness. Okay, okay. So we have L square Lm. So to find stiffness, this is stiffness for element 1. So what is L? L is 0 for element 1. L is 0. What is M? Is 1. So M is 1. So 0 to the power square is 0. 0 times 1 is 0. Minus 0, 0. This is 0, all 0. Okay. This one L times M, 0 times 0. This one M square, M is 1, so 1. Okay, so this 0 times 1 minus 0 times 1 is 0. This minus 1 square. Okay, 1 square. This, remember, this is minus maintain. Okay, the only square is 1, so it should be in the bracket square. Okay, this one is minus 1. Okay, it is not minus 1 square. It is minus square bracket and square the 1. See? Okay, remember about this one. Do not confuse. Okay, and this one 0, 0. This is also 0, 0. 0 square, 0. This is 0. And this one 0. This one minus 1 square, 1 square. Okay, minus 1 square. So 1 square is 1, minus. Maintain the minus. Okay, this is 0 and this is 1. Okay, so you get value for element 1. Remember EA over L. This is structure. You have to put EA over L. Okay. Okay. This is 10 to 10, 210 gigapascal. So change it to 10 to the power 9. Area is meter square. So 6 times 10 to minus 4. L is 1 meter. So we use meter. Okay. Pascal is Newton per meter. Okay. Okay. So note 2 for element 2. So similarly, we put all the value, and then we get this one, the Young modulus time the area over n, and similar to element 3. So we have element 1, 2, and 3. Now we have to assemble the 3 small kit. So we get this one. Okay, I have shown you how to assemble this the small k to make a bigger k in the previous lecture. Basically, you just identify node. They call it column 1, to column row 1 in the small k. Okay, so you see we have 0.5, 0.5. So this one at element at node 1x, to 0.5. We don't have it here. How about in the element 1? Element 1, 0. Okay, 0. So 0.5 plus 0 is 0.5. So we get this 0.5, and the rest are the same. Okay, same method. Okay, and the final set of question is k time displacement equal to force. K time displacement is for this. This is the fundamental equation. So we get k already. From here. Now, what is the displacement? on the boundary condition. Okay. So from the picture, we know displacement, global displacement for not one, global displacement 0, fixed 0, 0, 0, 0. For not 2, there is a displacement in x direction. So there is a displacement, but cannot move in y direction. So 0. Not 3, not 3. This is tricky, okay? Not 3 in global direction, okay? Global direction. Okay, this is in global direction, okay? In this direction. Okay, since at not 3, the node is inclined, it's moving in the x local, okay? So at the beginning, node 3 in the global coordinate is somewhere here, okay? For x value at node 3, global x-axis, d3x originally somewhere here, d3y originally is somewhere here, okay? From original x y axis, okay? And there is a force, node 3 will move, cannot move here, cannot move to x what x global direction, but because of this support here, we will move up, okay? We will move up, okay? When it move up to here, see what happened, okay? And there's a force, we will move here. Now the value of d3x is a new value, so d3y is a new value, so we know there is a value here. So we have to calculate what is the value for new d3x and d3y. Okay, so there is a value for d3x and d3y, but d3y in local in this axis, that there is no movement in this local y axis. Okay, this one is 0, but in d3x local axis, which is in this axis, obviously there is a value. Okay, obviously there is a value. So there is value for global d3x, global 3y, and local d3x. Okay, so we can say the boundary condition is d3y is 0 boundary condition. Okay, and we can transform this into global, to the global condition. Of course, because not one consists of x and y, we want to transform it using the transformation metric. We have to consider also the x value. Okay. Also for force. Okay, for force. Okay, force in 3x. Okay, in contrast to displacement, this is in 3x local, because not 3 can move in the local x-axis. So there's the force is 0. The reaction force is 0. Okay, but there is a reaction force in y. That's why it cannot move in y local. Okay. Okay, so we remember the step, identify the boundary condition. We already identified. Okay, at node 3, cannot move in y local, so 0. But force is 0 in x local. Why is 0? Because it is can move. There's no constraint. There's no reaction force in this direction or node 3. Okay, obviously there is a reaction force in y because there's support here. When there is a force, there is reaction force. Okay. Okay. So the reaction force for global, yes. Okay. F3x global, yes. F3y global, yes. Because you cannot move in global 3x, global y. Okay. Reaction force in global, yes. Okay. Transform the local boundary condition to global XY system using the transformation metric. Okay. So we do it in the next chapter. Okay. Okay. This is similar to this one. Okay. So transform. So we take the local and transform into global. Okay, or transform the global into local. The relationship between the two. So this is transformation metric. Okay, so we know this the value of L M. This is between uh, not 3. Okay, not 3. Okay, this is for element 3. Okay, element 3 from original. Okay, from original. So is L is 1 over square root 2. Okay, 1 over square root 2, 1 over square root 2. So we have the value. Okay, this one time this one time d3 dy. Okay, we get this one, and this one minus 1 over square root 2 times this one. We get this one and this one. Okay, so we get this one. Okay, yeah, see, minus d3x. So this one times d3y is this one. Okay, this one minus times this one is this one. Okay, so we get this one because it's d3x is no d3y is 0. This one is 0. Okay, so if we equate this one, we use this equation, d3y is 0, so equal to 0. Okay, so the square root go to here 0. So at the end, this d3y minus d3x is equal to 0. Okay, we have under the equation. Okay, for force, okay, force element not 3, element 3. Okay, so we get this one, and then we time this one times 3x, this one f3x, this one times 3y is this one. This is minus times this one, so this one. So we put it outside the 1 over square root 2. This one times this one is this one. Okay, this one is 0. So you know this equation, and then so this square root go to this side, times 0 is 0. So f3y times plus f3x is equal to 0. Okay, so we have another equation. Okay, so we have equation 1, the original one. From boundary condition, we have equation 2, and another boundary condition of force, we have equation 3. Okay, and we know K already. K here, our previous calculation. Okay, now we can solve. Okay, incorporate boundary condition and reduce equation 1. So in this case, it is not 3 and not 3. So the boundary condition is, we know boundary condition, another one is d2x. Okay, d2x, d3x. We know already from here, d3x, d3y. And then we have this d2x. So we have 3 unknown, d3x, d3y, and d2x. Okay, d2x. So we have 3 equations and 3 unknown. Okay. And then we solve it. Write this equation out explicitly. Explicitly mean clearly. Okay, obviously. Okay, write this equation out explicitly. Okay, so you get this equation, and the second one you got this equation, and from the third row you got this equation. Okay, take this one times this one from the first row to this one. 1 times d2x minus 1 times times d3x, 0 times d3y equal to p. So you get this one. Question 4. How about this one? This one is row number 2. Minus 1 times d2x, 1.5 times d3x, 0.5 times d3y equal f3x. Okay, so equal to f3x. So this is the original one. So minus 1.5, and this one. And the last one, the last row. Okay, you have this one, 0 times d2x, 0, 0.5, d3x, so 0.5 d3x, 0.5 d3y. So 0.5 d3x plus 0.5 d3y equal f31 with this one, okay? Okay, 0.5 d3x plus 0.5 d3y equal to this one. This is maintained. And now we solve it, okay? Add equation 5 and 6. So equation 5 and 6. So add this one, f3x plus f3y, f3x plus f3y. And then for d3y, d3y for this one. So it's 1. From 1. 1.5 plus 0.5. So it's 2. And then this is a minus 2x plus 0. So minus d2x. And then this is just maintained, okay? Because so from this equation, we know d2x equal 3 d3x. Okay, from this equation, we get this one. Okay. Now plug equation 7 into equation 4. This one, equation 7 into equation 4. This one. Okay, this one. Okay, so we plot it. Okay, because it's d2x is 3x. This one. So we can get d3x. Okay, so d3x is 0.00396. Then we can find d2x because it's 3 times this. 3 times this one. So 0.0119. Okay. And then from our equation before this, equation 2 and 3, we can find d3y. d3y is equal to d3x. So d3y is this value. Okay. Okay, now we have a value for displacement. We know the k already. D1x, d1x 0, 0 because fixed in all direction. Not 2, d2y is 0. d2x is here. Okay, already calculated. Okay, so we know this one and we know this one. And we can compute the reaction force. Okay, so we another matrix form, f1x, f1y, f2x is p, so 1000 kilonewton, f2x is p. Okay, f2y, the reaction force f3x, f3y, and that's a k, and we know this all already. Now we can find f1x, f1y, f2y, f3x, and f3y. Okay, so the answer is this one. It is good for you to do the detailed calculation, okay, on your own. Okay, okay. So obviously there is a reaction force, but not one reaction force in x and y. So this is the value. Reaction force at not one. There is a reaction force at not two in y direction. Y direction f2y. Oh no. F2y is 0. This is 0. F2y is 0. Okay. The value is 0. There is no reaction force here. But there is a reaction force at node 3 in x and y direction. Please do the detailed calculation and please confirm that this value. Okay. Okay, thank you very much for the attention, and we finish chapter 4, and inshallah we meet again for chapter 6. Okay. Assalamualaikum warahmatullahi wabarakatuh.